All right, so we're going to look at another integral, and we're going to see, once again, how we could use complex analysis to more simply solve this integral. Now, you might recognize that 1 over 1 plus x squared is the derivative of arctangent of x, and you could use the limits of arctangent of x and traditional integration methods to learn that this is just pi. But imagine you make a small modification to this form, or imagine that instead of this, you have something, maybe you don't recognize that this is the derivative of arctangent of x. Maybe you don't know the limits of arctangent of x as x goes to infinity. Then we could use our complex analysis tools to figure out what the value of this integral turns out to be. So, how do we know to use our complex analysis tool set on a problem of this type? Well, unlike last time, this is not a closed loop integral, right? This is an integral along the real line from minus infinity to infinity. So let's just go ahead and put this on our complex plane to see what's going on. We can plot any real function on our complex plane, and the domain of this integral is just going to be, if we represent this integral, it's only going to be on the real line. So we can't put points at infinity on our graph, but what we can do is we can put points like this. We can call this minus r to r, and eventually we can take a limit as r goes to infinity. So this integral is represented by this process. However, this is not a closed loop, right? So none of our closed loop integral rules are going to be valid for this kind of process. So what we have to do in order to use those tools is we have to add more segments to this path to make it a closed loop, and then we can use our tools on the entire loop and break it down into the parts and see how we end up getting this result. So, if we want to make this a closed loop, we have to connect these two endpoints. And you could do many different paths, but very often we just like to use circles because they're very easy parameterizable, right? If z equals r e to the I theta, we just have to integrate d theta to describe going from a point over here to a point over here along a fixed radius. So, what we've done here is we've made a contour, and I can write out our closed loop integral, and you can see how it's split up. So I'll write it over here. The integral around this entire closed loop, we're not looking at x anymore. We're going to be looking at complex numbers. dz over 1 plus z squared. This entire closed loop integral will be equal to our integral from minus r to r of dx over 1 plus x squared. That's our real portion of this integral, plus this half circle, where we're integrating from theta is equal to 0 to pi. So I'll write 0 to pi. And we need an integral with a d theta inside. So we have to take this function with z's and turn it into a function with thetas. And we did this a little bit before, right? We know z equals e to the I, let me include a radius here, r e to the I theta. So if we take dz, that was equal to I d theta r e to the I theta, or I z d theta. So, in other words, d theta is equal to dz over iz. And if we have this z squared here, we can rewrite that as, we can write z squared as r squared e to the 2I theta. Just squaring this normally, there's no absolute value, so we're not taking like the norm squared. So if we make these substitutions, dz we can see is equal to iz d theta, or I r e to the I theta d theta. In the bottom we have 1 plus r squared e to the 2I theta. So we've taken this f of z dz and we've turned it into a function of r and theta and integrating with respect to theta across this half circle. So you can see how our loop is built up. And so now that we have a loop, we can use the machinery that we've developed. And that machinery requires us to know, are there any poles inside of our loop? If there are no poles, no points where our function is non-analytic, no points where our function blows up to infinity, the closed loop integral is 0, meaning each of these segments combines to 0. If there is a pole, we use residue theorem, and so we have to check. All right. So if we write our function f of z is equal to 1 over 1 plus z squared, it's not too useful to us in this form, but we can see there is a denominator with a z, and if z squared is equal to minus 1, the denominator is 0, the function blows up. So we could factor this into z plus I and z minus I, or we were very close to just solving it by inspection to find the poles of I. And if we look at these factors, we can see if z is equal to I or minus I, that gives us a pole. So if we go back to our complex plane, one of those poles, positive I, is inside of our loop. So in this case, we have a pole inside of our loop. We need to find the residue at this point in order to figure out the value of our closed loop integral. So the way we do that, remember, is we go f of z times z minus z naught, evaluated at z equals z naught. Technically, it's the limit as z approaches z naught. And so z naught here is our point of interest. The residue at a point is equal to this. And so when we plug in our singularity of z equals positive I, we will get f of z times z minus z naught. F of z is this times z minus our pole, z minus z naught, which I'm just going to go ahead. Our pole is at I. These will cancel. If we plug in z is equal to I, we take this limit. Then, if we plug in z equals I, we have I plus I is 2I. Our residue is 1 over 2I, or if we write this in a better form, that is minus I over 2. And so our residue theorem tells us the closed loop integral f of z dz is equal to 2 pi I times the sum of our residues. Only have one pole, only have one residue, minus I over 2. If you work this out, I times minus I is minus I squared, turns into 1. The 2's will cancel. We just get pi out. So, in our big integral equation, we figured out the left-hand side. We know that pi is equal to the sum of these two integrals. Now, since we know what the final answer is, you might be tempted to say, well, I've done this, the answer is pi, that's how we get that. But it's not that simple. this integrand, I, capital I, is equal to this integral in red here, after we take the limit that r goes to infinity. So we haven't evaluated that yet. We have to solve this blue integral, and then if we subtract that from our result here, we'll end up finding the integral we set out to solve in the beginning. So, now that we've solved this integral to be pi, we need to solve this blue integral. So, we can do that without a ton of work, just by knowing that we're going to take the limit of this right side as r goes to infinity. That will set the limits of this first integral to infinity to make it exactly match our starting integral. And these r's inside our second integral will also tend towards infinity. And just by looking at the integrand here, we have a power of r in the numerator. We have a power of r squared in the denominator. So if we take the limit before we take the integral, in other words, if we evaluate it like this, I r e to the I theta d theta over 1 plus r squared e to the 2I theta, this value of r in the denominator is going to grow much faster than this value of r in the numerator. The value of 1 will very quickly become quite small in comparison to this second term. And so this limit evaluates to 0. And so we're integrating 0 d theta, and we end up getting that this blue integral vanishes. When we blow up this semicircle integrating from positive to negative infinity, it ends up vanishing and turning into 0. So if we wrote out this entire equation again with our known results, we have pi is equal to the integral from minus infinity, after we take the limit, dx over 1 plus x squared. Our original integral, this is capital I that we were trying to find, plus 0. And so if we rearrange, we get our result. This integral is equal to pi. So creative choices of contours, taking integrals that are infinite indefinite integrals that are on, or infinite definite integrals, integrals that are on the real line from minus infinity to infinity, or some finite value, we can add more portions to the path and use our rules for closed loops. We just have to be able to parameterize those extra paths and evaluate those integrals. If we draw funky loops and we can parameterize them well and we can take limits, a lot of integrals actually are very easy to solve. So you might end up having a system like this. You might have a pole on the real line, but you need to integrate from minus r to r. How do you do that if you have a pole here? Well, you could draw your contour, cut around your point here, and then integrate back around. And you would need to take limits as this small half circle contour shrinks to this point right here. If this was the only pole, you would know the entire loop is 0. You could try to figure out this half circle, what it integrates to. Maybe it blows up and turns into 0. Very often that's the case. And if you parameterize each of these points and you take the limit as this circle shrinks to 0, then you could evaluate this real line integral the same way. So complex analysis really helps whenever you can identify that there is a pole in your system. And we have to be careful. We have to make sure if we are taking limits as these things blow up to infinity, that we're not going to run into any other poles, right? Remember when we looked at the radius of convergence, the circle of convergence? If we had another pole out here, We wouldn't be able to take this loop and blow up the radius to infinity. It would hit this pole and would be non-analytic in this place where we're trying to take the limit. So you have to be careful when you're drawing your contours to make sure that you're not trying to blow up and take the limit of a contour past a pole or past a singularity. But parameterization and limits are your friend when you're dealing with these kinds of problems.